So first of all, let's denote the the new um, the new x and the current x. The difference between them will be pk, and the new gradient and the current gradient. The difference between them will be qk. So we know that from previous lecture that this is true, that the Hessian times the uh, differentiate of x is equals to differentiate of g. So you also want this to be to be true when there's an increment. Let's say from x k plus 1, like from xk to xk plus 1, it's it's like a increment on x, or yeah. So you also want it to be like this will be the increment on g. So there is something called scant equation that is based on this. And we'll also have if it's in terms of increment, this equation also holds. So now we want to approximate the Hessian. What should we do? We'll try to make this property hold from the updates. So what we're doing right now is we use something called rank 1 update, which means we use the current hk and two vectors, which is basically of rank 1. This is a rank 1 matrix. So if you add this on the current matrix, it's a rank 1 update. So we need to make sure that the new Hessian satisfies the scant equation, so it will be more close to the Hessian itself. So what should we do now? It's just we plug this in here, and then we have these two terms from before. So now we take out the u, the last term, we take this term out, and then we move everything back. So eventually we'll get u equals to this term, and v can be any vector, and the scant equation is going to hold. So now is the question that how we're going to choose v here. The most straightforward way is we want to keep the Hessian to also be symmetric. So the easiest way to choose is we simply choose the v equals to this term right here. So if we do so, then you can plug this back in here. You see there's a v transpose, and then you have a v right here, and then it'll be symmetric, and then this is only a scalar right here. So that's exactly what we do is we just pick this as v, and then we plug it back, and this will be the updated equation.